So, last time we had to stop a little abruptly with the following theorem. So, we want to show that there is no probability law on n such that P referring to the probability of a n is equal to 1 by a for all a in n. By a n we simply refer to the multiples of a for some specific natural numbers n. So, for example, 2 times n is just the set of even numbers. So, let us prove this, and here when I talk about probability on n, I am taking n, the sample space consists of the set n along with all its subsets. So, let us say such a probability exists. Let us prove this by contradiction. So, suppose P exists. Now, note this observation has nothing to do with P existing. We just note that if a and b are co-prime positive integers, then if you take the intersection of all multiples of a with the set of all multiples of b, you end up getting exactly the set of all multiples of a times b. I leave this as an exercise for you to verify. This is true, of course, only when GCD and of a and b are 1. Now, note that we have assumed that such a probability exists. So, note that. So, P of a n intersection b n therefore is equal to P of a b times n, which is 1 by a b by our assumption, which in turn is equal to P of a times P of b. And therefore, what this tells you is that when a and b are co-prime positive integers, then a n and b n are independent events. And so, from this it would automatically imply that n sub a, which you define as n minus a n. So, all those natural numbers which are not exact multiples of a, and n sub b, which is again defined as n minus b n, are independent. And therefore, what this tells you is that probability of n sub a intersection n sub b has to be equal to the product of the probability of P of n sub a times P of n sub b. But what is P of n sub a? It is just 1 minus 1 by a. So, this would just turn out to be equal to 1 minus 1 over a into 1 minus 1 over b. What does this mean? Suppose I want to take, this can be extended to any finite collection of these type of sets. So, now what we do is, let us take some natural number m, and let us fix this for a moment. and using the assumptions that we have made, we want to derive the probability of the singleton m. To evaluate these using the assumptions we have made above, we observe the following. If you have a prime p which is strictly greater than m, then m, the singleton m, obviously cannot be a multiple of the prime p, and therefore, this is an element of n sub p, and therefore, it is in the intersection of n sub p for all primes p which are strictly greater than m. Now, let us take, so what this means is that, so for some n such that m, so p is greater than m and p is less than or equal to little n. So, for such an n, what you have is that probability of the singleton m has to be less than or equal to the intersection of all the primes. So, suppose you choose any n which is greater than or equal to p, then clearly this probability has to be less than or equal to the product or the probability of the intersection of all the n sub p's, where p are primes lying between m and n, which by what we just learnt above is exactly equal to the product over all primes up to n and strictly greater than m 1 minus 1 over p. This is true for any n which is bigger than p. So, what happens as you let n go to infinity? That is the question, and this is a product that we have studied well. Pretty much a lot of the previous week went towards discussing this. So, what is our situation? Recall, you have log n, which by your integral test was equal to the sum of reciprocals of natural numbers up to n, give and take a small constant, right. And what's more, you also learned that k going from 1 to n, 1 by k, by a quick observation, this is certainly less than or equal to the following product, where each of the terms in the product is of the form 1 plus 1 by p plus 1 over p square and so on. So, if you have any natural number less than or equal to n, it can be written as a product of prime powers, where each prime is bounded above by n. So, this inequality is just encoding that observation in an analytic fashion, as we learnt last week. And so, this of course, you know, the inner product is just a geometric sum. So, what is this? So, product over all the primes up to n of 1 minus 1 by p inverse. So, you are telling me that this product is greater than or equal to this sum, which in turn is log n plus O of 1. Now, what does this tell you about the product? Here you now you do not have inverse, you have 1 minus 1 by p. So, notice that suppose now you take m is something fixed, 1 minus 1 by p. So, we can, it does not hurt us to multiply and divide by all the corresponding products for primes up to m. So, 1 over p less than or equal to m, 1 minus 1 by p. Since m is fixed, this is not something that we have to worry about. This is some fixed constant that depends on your choice of m. But now, in the what remains is the product of all the primes up to n, 1 minus 1 by p. Now, the inverse of this product is greater than or equal to log n plus O of 1. Therefore, this product itself is less than or equal to 1 over log n plus O of 1. So, to conclude, what we have is that thus p of m is less than or equal to 1 over product 1 minus 1 by p, where p runs over all the primes up to m, times something which is of the form 1 over a function which is very close to log n, give and take some constant. So, 1 over log n plus O of 1. What happens as n goes to infinity? M is fixed, so we do not have to worry about this part. This goes to 0 as n goes to infinity. And so, what you have told me is that if I were to take any fixed natural number m, the probability of the singleton set m is equal to 0, right. So, this means that p of m is 0, but you can start with any natural number m and do the same carry forward the same reasoning for that. So, this what this tells you is that this is 0 for any m in n, and this contradicts our assumption by the countability of the probability law. So, this is a contradiction, and therefore, very surprisingly, you cannot have any probability on the set of natural numbers which will take the value 1 by a for the set of all multiples of n by a, which is very counterintuitive. This is something that we would expect a probability law to satisfy, but there is no such. So, we have to overcome this limitation, and we do so with the help of the notion of density, which we will, I think we have all seen the definition of a density. We will define it again formally, and we will learn to interpret a density as a limit of probabilities, and the strength of the notion of density is that it satisfies those limitations which the probability law on the set of natural numbers cannot. So, this takes us to the topic of density of sequences in n. What we do is we start with a sum of non-negative real numbers. In fact, let us take positive numbers in such a way that this sum diverges. I am not going to take a finite sum, and each lambda sub n, let us say, is greater than 0. Now, what we do is, the reason we are taking this kind of a sum is these lambda sub n's are actually weights. So, we are going to attach weights to any sequence. So, given a sequence any any subset of n is a sequence, isn't it? Any countable, because it's countable. So, given a sequence, let us call this A contained in n, define D, let's just call this D sub lambda of A as follows. Let us first take, it is the following ratio, and we have, first we sum over all those n up to x where n lies in this sequence, lambda sub n, divided by all the n less than or equal to x lambda sub n, and define this density to be the limit as x goes to infinity of this ratio. So, it is in some sense measuring an intuitive notion of probability, not the formal notion, but intuitively with the help of attaching certain weights, it is counting, it is measuring the probability, so to speak, of some some n's up to x lying in the sequence A, but it is doing so by attaching weights to it. And why do we need to take a diverging sequence? Well, if you were going to take a finite, divergent sum, if you were to take a finite sum, what does that mean? The tails are going to 0. That means in your choice of weights, the maximum possible sizes or the weights sizes are in the first few weights. After that it becomes very, very tiny, rapidly decays, but that is not what we want. If we are going to really study a notion of density of a sequence, we want to attach weights to it, which are in some sense uniformly spread out across all the natural numbers. So, this is the reason we take a divergent sum. Now, of course, the most immediate example that comes to mind is lambda sub n is equal to 1. So, when you take lambda sub n is equal to 1 for all n, that gives you what is called the natural density. So, the definition of natural density is the restriction of this to the sum where each weight lambda sub n is 1. So, d of A is just, what does it turn out to be equal to? This is 1 whenever n is in A. Therefore, the numerator is just the cardinality of the set of natural numbers up to x for which, so which not lambda sub n, which also lie in the sequence in the sequence A, yeah, and divided by the number of n less than or equal to x, which is asymptotically same as x goes to infinity. So, in the denominator we can replace this by x. So, this is your natural density. Now, we are banking upon this notion to overcome the limitations of probability. So, now the question is, let us take the set of all multiples of a specific natural number A. So, define A to be equal to A times n. The question is, what is the density of A and how will you measure it? So, A n, actually not just, let us do something more general than A n, and A n will be a special sub cases. Let us actually consider the set of all, let us consider arithmetic progressions. Okay. So, let us consider all the n in the set of natural numbers such that n is congruent to some L mod A, where what are the things given to you? A is some fixed natural number, and L, actually L could be any natural number, but we are going to reduce it modulo A to, so A minus 1. So, now the question is, so for a specific L that lies between 0 and A minus 1, and for a specific A, this is the arithmetic progression we are taking. Now, the question is, suppose you have to count the number of n up to x which lies in A. So, if you have an n in A, what does that mean? It can be written as, so it can be written as AQ plus L, right. Typically, in this course we are going to use Q to denote prime numbers. So, let us just call this some other number AM plus L, and we also want this to be less than or equal to x. So, we are counting all possible n's which can be written in this way up to x. So, we are going, in other words, we are going over all the m which are less than or equal to x minus L over A, which is, by now we all know that this is just x minus L by A plus O of 1. Therefore, what this means is that d of A is just the limit as x goes to infinity 1 over x times x minus L by A plus O of 1. What is this limit? Now, notice L and A are fixed numbers. So, L by A just gets absorbed in the O term. So, you have x by A plus O of 1, and then you are dividing it by with 1 by x. So, you have 1 by A plus O of 1 by x, and x goes to infinity, O of 1 by x is just going to 0, and therefore, you are just left with 1 by A, which is what you wanted your probability law to satisfy. There was no such probability law. So, you define the notion of a density. Okay, now, this notion of a density can actually be interpreted as a limit of probabilities. This is actually the fundamental, one of the most fundamental ideas in this course. By the way, there are some other types of densities as well. So, there is the logarithmic density, where you take lambda sub n is equal to 1 by n, that can be compared to natural density. And then there is also the notion of an analytic density, which we will discuss later. So, relation between density and probability. Let us do the following. So, what we do is, so we have got the set of natural numbers, and we are going to break it down into finite sets. So, first what we will do is, we will take the first n natural numbers and let n become bigger and bigger. So, recall you had studied in the previous weeks, you can take the finite set n, equip it with the uniform probability, meaning the probability of every element in this set is exactly equal to 1 by n. So rather, and we call that nu sub n. So, mu sub n of each I is exactly equal to 1 by n for each Let us now induce a probability on the set of all natural numbers using this. What is that? So, now define P sub n on n to whatever your by P sub n of any I, will just take the value induced by your mu sub n on I if I lies between 1 and n, and for any I greater than n, just make it 0. You can verify that this is indeed a probability law on the set of natural numbers, and what you also observe is that your density of A simply turns out to be equal to the limit as n goes to infinity of these probabilities, which are induced from probabilities on smaller sets. So, a density can be interpreted as a limit of probabilities. Now, when you have a probability space, you discuss, we study random variables on them. Our goal, as I have repeatedly mentioned, is to use probabilistic framework to study the behavior, or in other words, the value distribution of what we call arithmetic functions. Now, most functions that we actually take would be real valued, but in general if you have a function that can take complex values on the set of natural numbers, that is called an arithmetic function. Had n been a probability space with the kind of probability that we want on it, then we could have considered this f as a random variable on that space. So, just for clarity, let us actually quickly review the notion of random variables. So, let us take a space omega be a sigma algebra on omega and P a probability. So, let this be a probability space. A function x on omega is called a random variable on our space if what happens is if the probability of the following set, all those t in omega for which x of t is less than or equal to x. Okay. So, if for any x in R, the probability of the set, rather actually if we do not need the notion of probability in the definition of a random variable, if just this set will lie in your sigma algebra. Now, in the case when we take omega to be the set of first n natural numbers and the sigma algebra to be the set of all possible subsets, then this is not you can basically any function on that set will be a random variable, but this is the more general definition. And what we do is, so notice in the definition of a random variable you do not need the notion of probability, right. You just need to know your sample space, your omega and your sigma algebra. Now, with this in place, so what we now say is, so let's give a quick example. For example, suppose we define what is called the indicator function. This is a function that we will repeatedly encounter. Define this to be equal to 1 if t is in A and 0 otherwise. We also denote this as the characteristic function of the set A. So, A is in omega. This function will define a random variable if and only if your A will lie in your sample space. It will be in your sigma algebra. So, this is an observation I wanted to make. Now, we recall the notion of a distribution function and the notion of a distribution function corresponding to a random variable. So, in general, a distribution function which we denote as capital F is a function with domain R, okay, and going to the interval 0 to 1. So, this is a function such that what happens? You want A F is right continuous and monotonically increasing, non-decreasing. So, F is non-decreasing and right continuous. This is the starting assumptions that we are making for the notion of a distribution function. And the other assumption is that as x goes to minus infinity, limit f of x goes to 0 and as x goes to infinity, f of x is equal to 1. So, whenever we say that something is a distribution, this is what we mean. It is a function from R to the closed interval 0 to 1 satisfying these properties. One of the strongest examples of a distribution function is that corresponding to a random variable. So, a distribution function for or corresponding to a random variable x on the space that we are working with is the following function, is defined as the probability of the set of all those t in omega for which capital X of t is less than or equal to x. We already saw from the definition of a random variable that this set is in your sigma algebra, and this is what we define as capital F of x. You can verify that this function f will satisfy the conditions above, and a shorthand notation of this is that capital F of x is equal to probability of capital X less than or equal to x. This is your shorthand notation for this function. So, now what we do is we take some arithmetic function. I am going to talk about real valued arithmetic functions. So, let us take this. Now, what we do is we denote from f, we go down to the set function f sub n, which is defined on the set of the first capital N natural numbers, right. So, we define this as 2r. So, f sub capital N of x is just f of x in this set. So, we are just descending from a set of function on the set of all natural numbers to functions on the set of the first capital N natural numbers. With this, and by equipping this set with the uniform probability, this can be interpreted as a random variable on the space. So, your f sub n as n goes to infinity is a sequence of random variables. So, now what we do is for each capital N define the following. Define the following distribution function as the following. So, capital F sub n of z, define this to be equal to the probability on, so the uniform probability on this set we have learned to denote as nu sub n. So, define this to be nu sub n of all those n for which f of n is less than or equal to z. This is how you define this capital F sub n of z, which is by definition, what is this? This is just your 1 by n into the number of n's for which f of n is less than or equal to z. No rocket science happening here, we are just formulating the language. So, this is basically your distribution function corresponding to the random variable f sub n. Fine. Now, we say that all of this has come from your original arithmetic function. So, we say that f from n to r has a limiting distribution function let us call it capital F, if limit as n goes to infinity of capital F sub n of z is equal to capital F of z. So, suppose there is a function capital F such that when you take the limits of f sub n as n goes to infinity, okay, so it is actually, yes, let us stick to the notation that we have, does not matter, but still. So, this is equal to this exactly equal. So, if there is a function f which matches these limits for all z in C of f, what is C of f? All points of continuity of f. So, if such a function exists such that the limits of these capital F sub n's matches this function f, at this capital F may not be, need not be continuous everywhere, but at the points of continuity this equality holds, then we say that your arithmetic function that you have started off with, it has a limiting distribution function. So, we do not talk about a probability on n, we talk about a density of on n, which we saw can be interpreted as a limit of probabilities. Similarly, on a random variable on a probability space, we talk about distribution functions, but in our setting, since we do not have a probability space on n of the kind that we need, we talk about limiting distribution functions. This is the fundamental comparison. So, in an ideal world, as there is this very beautiful lecture on YouTube by Professor Desuyer, and he says, so the ideal world is the probability world, the probability model, and the real world is the world in which we are living, the world of arithmetic functions. I hope you agree that a world of arithmetic functions is our real world. This is the world we live in. So, we have this notion of a limiting distribution function, and this is another way to say this is that your little f has a limit law. Okay, if such a function exists, we say that f has a limit law. So, what are we going to learn? We want to learn how to use theorems from probability on probability spaces and random variables and translate them into theorems related to densities and limiting distribution functions corresponding to arithmetic functions. This is our goal. Okay. By the way, since we have worked hard and defined a proper probabilistic notion as well, as I had mentioned above, for random variables on probability spaces, we can talk about the expectation and the variance. So, what does that mean? So, let us take, so given f, I am going to, so the notation f comma mu sub n simply refers to, you are taking an arithmetic function, considering it only in the set 1 to n equipped with the uniform probability measure. That's all. So, what is the expectation of f? By definition, it is equal to 1 by capital N summation I going from 1 to n f of I okay. What is the variance of f? It is 1 by n summation, so little n going from 1 to n, take variance studies the amount of deviation from its expected value, right. So, f of n minus E of f, here we denoted it as E of f whole square. This is your variance. And then we learnt, particularly if you take f to be the prime omega function, then what happens, and we came up with certain estimates, that is the theorem 0 of probabilistic number theory. We now want to do that, we want to play that game for a larger class of arithmetic functions. To begin with, let us focus on additive functions, and we want to develop a general theory out of which the Hardy-Ramanujan theorem will fall out as a special example. At this point, I want to define the notion of a normal order. Since we are talking about an average order and we are talking about the variance, the question is, how close is a typical, for any specific little n, how close is f of n to its expected value? Does the expected value or the average order, as we saw before, is it very far away from f of n, or would you normally expect f of n to be very close to it? So, this takes us to the notion of a normal order of an arithmetic function. So, an arithmetic function f is said to have normal order equal to some function g if the following happens: for any epsilon greater than 0, however small, the inequality absolute f of n minus g of n less than or equal to epsilon times g of n, absolute g of n, holds on a set of natural numbers of natural density 1. So, almost all, holds for almost all natural numbers in that sense. So, for any epsilon greater than 0, if this inequality holds on a set of natural numbers with natural density 1. That means the set of natural numbers for which this inequality does not hold goes to 0. The natural density is exactly equal to 0. So, other ways of stating this definition are as follows. So, that is, for any epsilon, so limit, for any limit as n goes to infinity of 1 over capital N times the number of 1 less than or equal to n less than or equal to capital N, such that absolute f of n minus g of n is less than or equal to epsilon times absolute g of n. What is this limit? We want this limit to be exactly equal to 1. All right. In other words, so the above definition implies another way of writing it using the language of orders that we have learned is that f of n is equal to g of n plus little o of g of n almost everywhere, okay, on a set with natural density, which I will just write as density now, 1. This can also be written as 1 plus little o of 1 g of n. So, for any little o of 1, so what we are saying is that another way of interpreting this is that for any epsilon greater than 0, f over g, provided that is well defined, okay, the absolute value of f over g is bounded above by 1 plus epsilon. So, what it says is that, so let us now assume that f and g are both positive. Just for simplicity, let us assume they are both strictly positive functions. So, let f and g be positive functions and g is f has normal order g, then what does that mean? That means that 1 minus, so for any, this is very interesting, for any epsilon greater than 0, if you have, so this inequality f of n over g of n is greater than 1 minus epsilon and less than 1 plus epsilon, it holds almost everywhere. So, whenever we say that it holds on a set with density 1, short form of saying the same thing is holds almost everywhere on n. So, if this inequality, whatever epsilon is, it could be something very, very close to 0, so holds almost everywhere on n or with respect to n. There are different ways of saying the same thing. So, the values of f and g for almost all the natural numbers come very, they get clubbed very, very close to 1. Now, from this you deduce a really a nice property, which is the following. Suppose you have some number which is strictly less than 1. What is this following limit? Limit as n goes to infinity 1 over n times number of n up to capital N for which f of n is less than or equal to z times g of n. What is this? What do you think this limit should be if z is strictly less than 1? So, let us say this is 1, let us say z is something less than 1. You can choose epsilon such that 1 minus epsilon and 1 minus epsilon lies to the right of z. But you are saying that for almost all n in n, the f by g lies in this region, therefore, this limit must be 0, right. And what happens if z is something strictly greater than 1? Let us say z were, let us take some z prime which is greater than 1. Again you can take some epsilon, so that 1 plus epsilon would lie to the left of z prime, and you know that for almost all, for that epsilon, almost all the natural numbers would lie in this region. Therefore, if z was strictly greater than 1, then this limit would just be equal to 1, all right. And therefore, the limiting distribution function of this, of f by g, when f and g are, let us say, both positive functions, is exactly equal to the indicator function on the interval 1 to infinity. So, thus, okay, if f and g are positive, both positive functions, and f has normal order then the limiting distribution function of f by g is the indicator function So, these are nice ways of understanding normal orders. And here is another quick observation from based on whatever we have learned about the different distribution functions for prime numbers. Let us denote, so I am going to let you think about this. One thing we have learnt is that the set of primes, so we learnt last time that pi of x is O of x by log x. So, in other words, pi of x, that is enough to show that primes have density 0 on the set of natural numbers, and therefore, from that let us define the following function. So, let us define the function to be equal to pi of n minus pi of n minus 1. So, this will pick up the value 1 exactly when n is a prime, and otherwise this will just be 0. That is why we are calling it the indicator function on the set of prime numbers. What do you think the normal order of this function should be? Using the fact that primes have density 0 in the set of natural numbers, check that the normal order of this function is just the 0 function. Now, we have proved a certain theorem about omega of n, and it is supposed to tell us, eventually it will tell us, that the normal order of omega of n is log n. We are coming close to that, we have not entirely proved that theorem. So, to do that, what we have to do is, we are now going to study a set of a very important inequality for additive functions. Let us take the following function. I am not sure if I defined it formally, but let us take f from n to r. Let this be an additive function. What do we mean by additive? By additive we mean that if m and n are co-prime to each other, then f at the product of m and n is equal to f of m plus f of n. When we say multiplicative function, then f of mn has to be equal to product of f of m and f of n, but in the case of an additive function, we have the addition law. You can verify that omega of n is an additive function. It is the basic prototype of an additive function. Now, whenever you have an additive function, using the unique factorization of a natural number n in terms of its prime factorization, in terms of its prime powers, we can expand f of n as a sum of the values taken at its prime powers. So, a couple of quick notations. So, we say that all the symbols are going to denote non-negative integers. So, we say that, and p denotes a prime number, p raised to the some nu double divides n if nu is the highest power of p dividing n. So, if p raised to the nu divides n and p raised to the nu plus 1 does not divide n. Okay. So, using this notation, you can write n to be equal to product over all the primes, okay, with p raised to the nu. So, we need to specify the power for each prime. Let us call that nu of p, okay, corresponding to n. So, if you want to be even more specific, you say nu of p comma n. But all that we want to know from this is, this implies that if your function f is additive, this is equal to summation over all the primes dividing n f of p raised to the nu of p. We also have a stronger notation of a strongly additive function. So, an additive function is said to be strongly additive if, irrespective of the prime power that you are doing, f of p raised to the k for any k is exactly equal to f of p. So, is said to be strongly additive if f of p raised to the k is equal to f of p for any natural number k. So, f of p square, f of p cube and so on are all equal to f of p. And example is again our favorite function, the number of distinct prime divisors of n. You can verify this is indeed a strongly additive function. So, Now, suppose I want to using the probability spaces that we have defined above, that we already defined before, what is the, so given f, so far we have done all of this for omega, but for a general, let us even assume that it is a strongly additive function. So, what is the E sub expected value of f in the space of natural numbers up to capital N? So, 1 by n summation n less than or equal to capital N f of n, but because of additivity you know that the inner thing can just be written as product of all the primes, product over all the distinct primes dividing n f of p raised to the nu, where in fact p raised to the nu is the highest power dividing n, and if your function is also strongly additive, this is just f of p. And by now you are familiar with this template of calculations to know that you have to interchange, and what do you get? Of course, when you were doing omega of n, this thing was just 1, right. So, what do you have? Oh, not product, sorry, I am talking about additive functions. So, you have sum over all the primes dividing n f of p. And so, you interchange, and what do you have? You go over all the primes up to n. What should you have? F of p, and in the inner sum you will have all those multiples of p which are less than or equal to capital N, which is just our greatest integer function n over p. This can again be written as n by p plus O of 1, and this gives us a candidate, this calculation, generalization of what we have done for the prime omega function. It gives us a candidate for the average order and possibly also the normal order of your function f. But this is just a candidate, we do not know whether the candidate qualifies or not. So, now before we conclude for today, I want to give you a small exercise. Let us do the following. Let us define the following random variable, so corresponding to any prime power which is less than or equal to some capital N. Define a random variable corresponding to this from the set of natural numbers up till n to r as follows. In fact, not just r, this will be a Bernoulli random variable. So, it will only take the values 0 and 1 as following: x sub p raised to the nu of n is equal to 1 if p raised to the nu is the highest power of prime dividing n. So, even for smaller primes, this will it will fetch you 0. So, if p cube is the highest prime power dividing your n, then for n equal to p square you will still have 0. For n equal to p you will have 0. It is only at p cube that you will have 1. So, and then 0 otherwise. What I would like you people to think about before we start the next class is, what is the expected value of your random variable, okay, and what is another thing, suppose you have two distinct primes p and q which are not equal to each other, what is the expected value of the product of x sub p to the nu times y sub p raised to the nu. and you will see once you derive the expected value of these variables, you will start to see that these are behaving in a very similar manner to geometric random variables with certain parameters. Okay, but before that, please do this calculation and we will take this up in our next class. So, I will stop for today.